the Master's in Science from the Center of Research and Advanced Studies, CINVESTAV, from Politecnico as well, Instituto Politecnico, and the PhD from the University of Rome, La Sapienza, in Italy. In 1981, well, that happened in 1981. In 1985 and 1992, respectively. He worked as a lecturer at the School of Electric and Mechanics Engineering of the Instituto Politecnico Nacional from 1985 to 1989. From 1985 to 1995, he was at the Automatic Control Section of the Department of Electrical Engineering of CINVESTAV, and since 1995 at CINVESTAV Campus Guadalajara, where he was the director from 2010 to 2015. He has held several research stages at University of Rome, La Sapienza, University of L'Aquila, and he was a visiting professor as well at the laboratory. This is in French. My French is not very good. So, Laboratoire d'Automatique. No, I cannot say it. Sorry. It says LAAS of the French Council for Scientific Research, CNR, and at the University of Compiègne, among others. He has authored and co-authored more than 100 papers on journals and conferences, and has supervised about 20 PhD and 50 master students. He has also led several projects on basic and applied research, some of these with industry funding. His main research interests include nonlinear control design, hybrid systems, and applications of artificial neural networks and fuzzy logic techniques to control and fault diagnosis of dynamical systems and UAVs. He is a senior member of the IEEE and holds the level number 2 of the Mexican Researchers System. So please join me in a round of applause to Professor Bernardino. Yeah, I'm sure you will find his talk very, very compelling. So thank you, Professor.
Thank you. Well, thank you for inviting me, and thank you for applauding me before, because I have been in other talks and they don't applaud me after the talk. So this time I got it. I apologize a little because I prepared before a talk with this name, which surely you recognize, but I decided to keep the title, just for fun. We in my laboratory with my students, we have been working for some years in the area of drones. And when we started to work with drones, we decided to construct our own drones. This was a decision because we wanted to gain experience on what a drone was at that time. And instead of simply buying a drone and using it, we decided to construct one of them. And we started with not electrical, these are combustion motors with some tests, and which, by the way, didn't work very well. But anyway, after we switched to electrical motors, which seems to work more or less better. And we after constructed one quadrotor, and this was the quadrotor which flew many hours and now is retired with honors. This was our first really functional drone. After that, after gaining the experience, we decided to buy some other drones. And this is because we have a problem here in Mexico, because we are not competitive if we want at this moment, for example, for constructing drones. Because, for example, as far as we use glass fiber, carbon fiber, excuse me, we don't have here in Mexico who can construct this drone, except the army. No, except the army. But we don't have commercial providers for this kind of systems or structures. So we, even though we have a design, we are seeking for a builder for this drone, and we hope we will find some builder for this structure in the near future. I will this is a video that was made by my students because we started with applications. So what I am going to show here is some applications that we have been working with. Some of my students, and and this is the CINVESTAV, the CINVESTAV building in Guadalajara. And they decided to call this the laboratory of autonomous vehicles. Okay. And this is one of our first flight attempts. We started from the very beginning with outdoor flights, not indoor. We decided to do this because many of applications are outdoors. So this is a place in which we can fly all these aeromodelism planes and so on and so on. And here we are testing our first basic controllers. This is a PID controller for stabilizing the drone, so it works without wind. And we are testing, for example, controlling the position even if we pull the system, this come back to the desired position. Okay. And we started to no, it doesn't work. Anyway, and here we started with higher flights just to test the stability of the system. And this is our first quad. This was constructed by us. It functioned more or less well. Okay, we tested several things. Maybe I can just to go ahead. And this is just to show that the flight was autonomous. We simply choose a trajectory and the quadrotor was flying. This was our first autonomous flight with a drone. Probably CINVESTAV. Okay, I think I will skip this one because I'm going to talk briefly about drone control because I had to change the focus of the talk to drone control. So I will present here two algorithms for drone control that we have been working with. After I will mention other techniques that we are working currently. The first one is, this is the quadrotor, and this is just all the geometrical setting for obtaining the model. Maybe you know how to obtain a model of a quadrotor. And, how to control the quadrotor is we use 4 input signals. The first signal is the vertical thrust exerted by the 4 rotors. The second input is the difference of thrust between the left and right rotors. The third input is the difference between the front and rear rotors. And the fourth is the difference between the clockwise turning and the counterclockwise turning rotors. This is the way a quadrotor flies, because in order to, for example, if you want the rotor to go ahead, so you have to down the speed of the front rotor and increase the speed of the rear motor. And so this causes a difference, and so you can have all the movements manipulating these 4 inputs. So this is the model of the system. You can see that this is a very nonlinear model, just to mention the nonlinearities of the model. And you can choose to fly a quadrotor manually, obviously, but this requires certain capabilities of the user, no? Because he needs to be very sensitive to the inputs, to the electrical motors, and so on, so on. So, or to design a controller on the basis of the mathematical model. And that's the way that we are working to control the quadrotors. By the way, these are some regulations that in other talks the regulations were mentioned. And for example, we are not allowed to fly quadrotors over cities because it's very dangerous, etc. You can see this. Okay, the first of the algorithms is an algorithm based on fuzzy logic, and I will explain briefly what fuzzy logic or fuzzy controllers are. In general, we know that a good theory must be capable of gather all possible information in an efficient manner. Problem is that a mathematical model only have information of the mathematical model or the signals coming from sensors, and that's all. And those sensors, in the vast majority of the cases, are electrical signals, and that's it. Electrical signals. But in general, in the real setting, in the real life, we have 2 sources of information. Information coming from physical sensors and information coming from expert human knowledge, which is empirical. In fact, in the previous talk, the reinforcement strategy, what does is taking experience from previous attempts, right? And fuzzy logic takes this information. For example, I don't know, you want to control, heater, for example, in Pemex, let's say. So, in general, the engineer in charge of of the heater knows how the process behaves. And he applies this knowledge in order to move the valves or whatever he has to do. But if a new engineer or newcomer engineer tries to do the same, he won't get the same result in general. So human experience is important also. And that's what the fuzzy logic techniques does. So a fuzzy system is based on the knowledge of rules expressed in natural language. I will give an example later. In general, a fuzzy logic controller has this, how is it? Seems that this is running out of order. Okay, I have one here. So a fuzzy logic controller has several components. The first component is the fuzzification step, in which all the information that comes from the outside of the system is interpreted in a certain way. So it's fuzzified. We will see an example later. We have an inference mechanism which decide how to take control actions. We have some fuzzy rules, and after we have a defuzzification step, which convert all these signals to a signal that the plant or the actuators understand. In general, these are maybe electrical signals or whatever. So, and we have a feedback here, and this. So, fuzzy rules are quantification in terms of fuzzy logic of the expert's linguistic description. For example, this is a typical rule. If car speed is high, then apply less force in the accelerator. This is a rule expressed in natural language. By the way, in general, we, human beings, our behavior is in terms of these kind of rules. We all the times are deciding, if I do this, this is, obviously we are not thinking on this rule, but our brains act like this. If, I know, for example, this is a typical setting. If you're driving a car in a highway, and you know that you have to get out in somewhere, but you don't know exactly where. So at each output that you see, you are tempted to take this output. And if you don't do that, you wait until the next output, and you do the same. If I then, sometimes our brain jumps. And I don't know if sometimes you see a car in the very middle of the two spaces, on the highway and the output, and because their brain jammed and they cannot take a decision, and they go in the middle. Sometimes happens this. I have seen that. For example, this is an example of fuzzy rules. We have here car speed, we have low, medium, or high. Obviously, for each of us, this could be different because, for example, for my grandpa, if I say that 75 is medium, that's not true. Maybe for him, 50 is high. But for a younger guy, For him, maybe 95 is low. No? This is the knowledge from the user, from the expert. So what we do is to make a partition of the universe, what we say the universe of this course, in some sets, as many as we decide to take. In this example, we simply take three sets. And we decide, we have membership function. In classical logic, we have a binary logic, or you are in or you are out, right? For example, if I ask if you are inside the auditorium, the answer is yes, I am. And so your membership function is 1. And if I ask if you are outside, your membership function is 0. This is a binary logic. But for example, we can say that you are 60% here and 40% outside. In fact, at this time, this is the last talk, some of you are trying to sleep. So maybe you are 60% here and 40% outside, okay? And this is the difference with the traditional logic. For example, here we have this membership function for this example, okay? This falsification is a mapping from a real value in a certain domain to a fuzzy set in the domain. What the falsification does is to transform the values of the input into information that the inference mechanism can use to activate the rules. For example, we have several types of falsification. Singleton, which is 1 if the information coincides, or 0 in another case. But we have Gaussian, triangular, etc. There are several types of falsification rules. Just for example, we have an inverted pendulum. In this case, for example, we can say that we take the error, which is the angle between the vertical position and the angle of the pole, and the derivative of the error. This is very much like a PD, okay? It's very much like a PD. So we can choose, for example, we have negative big, negative small, 0, 0, positive small, positive big, etc. And the input is a longitudinal force. This applied to the car. And we have several cases. For example, we can say that we can have situations like great positive error, I don't know, great positive error, and I don't know what is that. What is that? Here, I cannot see. Okay. Anyway, for example, we can have positive error, which means that the pole is to the right and a small angle. So we define all our rules, which incorporated the expert knowledge. No? By the way, this is the game that we all the children do with a broom. No? You remember that? That's this system, exactly this. Let me show you an example. Let me show you. So this is the application of a fuzzy logic controller to the balance of a You remember this system is the Pendubot system, the same system. So as you see, it's very effective. So in just one movement. This is a fuzzy logic controller. There are several types of fuzzy controllers. This is what is called a Mamdani type controller, which is very simple. You see, for example, interesting, sorry. And it's robust. So it tolerates some perturbations, you see? Okay, this is a fuzzy controller. But as we are control guys, unfortunately in the control community, we cannot publish a paper if we don't have a theorem and the formal proof of the theorem. That's it. So we cannot publish a paper with this controller. That's the problem. So we have to go beyond the simple fuzzy controller and take a more sophisticated controller in which the mathematical model is considered. And that's what we did. I'm sorry. So we use the what we call the Takagi-Sugeno fuzzy model. This model incorporates the nonlinear mathematical model. So basically, we have some rules, and for example, if certain variables are in certain fuzzy sets, then the inference mechanism, instead of choosing empirical rules, it takes a linear description. A linear description. This is more or less, think about a nonlinear system which is linearized in different equilibrium points. So for each equilibrium point, you get a different linear system, right? That's it. So the same nonlinear model is valid, or it's very similar to the linear model, but for different equilibrium points. And that's what the Takagi-Sugeno fuzzy model does. So it describes a nonlinear dynamics locally with, I'm sorry for this. I don't know what happened. Sorry. We have a nonlinear system here, and we have linear descriptions for the same nonlinear system, okay? So, what we do with this, by the way, I don't know if you know or have you heard about switching systems. So systems that switch from, depending of the state of certain variable, switch from one description to other description. And these are switching systems. For example, the automatic, for an automatic car, it changes from the first to the second to the third, and each speed has its own mathematical model. So that's a switching model, switching systems. So this is like a switching system if we had a singleton switching policy. For example, if I switch from this linear system to this linear system to this linear system, then we have a switching system. But if instead I decide to describe, for example, in a certain region, 60% of this and 40% of this, then we have a Takagi-Sugeno nonlinear model. And this is an aggregate nonlinear system, which is described by this equation. So your original nonlinear system now is described in terms of linear models, but let's say modulated or weighted for this function, which are the membership function, depending on which region of the, let's say, of the state space the system is. Okay? It seems very complicated, but it's not, at least for me. So, in this system, we have the state of the system, inputs, and some external signals, which can be perturbations or can be reference signals to be tracked. Okay? So we have here the reference signals. And we assume that the reference signals and the perturbations are given by an exogenous system, given by this equation, and we have the output given with that. I'm very energetic today. Okay. And this is the aggregate system taking a singleton falsifier, probe inference, and center of gravity defalsifier. This is a specific choice. Problem here, a very, very difficult problem with this kind of model is stability. Stability. Because we can have stability of the original nonlinear description, but when we are here, we cannot take the same stability conditions. So we need specific stability conditions. Okay? And some of these conditions is that we need a matrix P which satisfies these couple of equations. Maybe some of you recognize this very, very famous equation. This is a very famous equation, right? This is the Lyapunov equation for stability. Very famous. Maybe it's very famous. In control community, it's very famous. Lyapunov was by 1920-25 was the first who introduced this kind. And this is not more than saying that it exists a kind of convex surface. You know that a convex surface has a minimum, at least one minimum. It can have some local minimum, but at least a local minimum. And what we say is that the state of the system flows on this convex surface, and at the very end, it's like a marble. You know, marble. You put a marble in a cup, the marble eventually will go to stability. That's it. That's the famous Lyapunov equation. And this is Lyapunov equation, but specifically for this system. And this is, the problem here is the higher number of linear matrix inequalities, because these are linear matrix inequalities. Maybe I'm a little bit technical, but anyway, let's try to go ahead. So, problem here is that we get a high number of LMIs, and this is a very hard computational problem, because it's very heavy. So we need problem is that for example, if you apply the computational algorithms to test the existence of this matrix, and you don't get a positive result, it doesn't mean anything, because it still can be stable. I don't know if you understand this. So it is just necessary, but not, it is sufficient, but not necessary. Okay? For controlling, we use this kind of policy, which is called the parallel distribute control, PDC, which is the same for all the controllers gates. You remember that to pull or to move or accommodate the poles of the system, the poles, you remember, the poles are the characteristic polynomials of the transfer function of the system. So the zeros of that polynomial are the poles. So you can accommodate by feedback those poles. And for the case of fuzzy systems, so we use the same policy, but now we have here the membership function, and that's it. Okay, now we have applied, the first attempt was apply this technique to the quadrotor model. So we have here the nonlinear model, and with all the state, which are the original position, the velocities, and some other quantities. So, and we applied basic regulation. So this, maybe I am bothering you, all of you, with these technicalities, but anyway. The final of the talk is more interesting, trust me. So don't escape. So we have a nonlinear system, and the problem of regulation theory. By the way, and this is simple for all, even if you are not in the control community. The problem of control a system is find a surface on which the tracking error is 0. And to find a feedback which makes this surface invariant. I don't know if so to find a surface and make invariant this surface. And the zero, the tracking error is 0 on this surface. How to do this? We have a lot of techniques to do this. A lot. Adaptable control, fuzzy logic, neural nets, whatever technique, reinforcement techniques, etc., etc. But the basic control is to find this surface. So, how to find this surface? That's the real difficulty in control theory. That's the real difficulty. And this setting, what does is to assume the existence of dust. So this pi of W is the surface, which is made invariant. This is an equation which expresses an invariant condition. No? So what we have is that the behavior of the system, the flux of the system, goes to this surface. But we want that the tracking error, the difference between the output of the system and the reference signal, is 0. And this is expressed by this equation. This is the error. Here we have the error here, and we want the error to be 0 on this surface, which is called a submanifold in general. For nonlinear setting is a submanifold. Submanifold is the extension to the nonlinear setting of the concept of linear subspace, okay? Linear subspace, okay? So for linear systems, these are the questions which are famous also in the control community. And this is the control signal, and for linear system is this, and I call this problem the problem of the guy who wants to dance with the beautiful girl who is sit in front of him. No? This is very famous. The problem of the guy who wants to dance with the girl, basically. So the first problem for the guy is to approach the girl, right? To dance with the girl, he has to approach the girl, and this is this part. This is the difference between the guy and the girl. So the guy has to apply a certain effort to reach the girl, okay? But now he has to dance. The problem is that he has to dance at the same move that the girl. So if the girl moves in a very nice frequency, let's say frequency, so the guy has to dance at the same frequency. If he is not able to dance at the same frequency, so he is dead. And this is this part. So the guy has to dance at the same frequency that the girl. So this is, obviously I'm kidding, but this is the problem of the guy who wants to dance with the girl. This is the problem of regulation. It's a very important problem in the control theory, okay? There are a lot of papers dealing with this problem. So what we did here is transform the nonlinear setting to linear setting by means of the fuzzy aggregated approach. That's it. And that's it. So for the specific case of the quadrotors, okay, I will not bother you with all these technicalities. We have here the values for the specific quadrotor. We have here the membership function that we choose. These are the angles, the Euler angles. And we have here, we have choose these reference, which are sinusoidal trajectories. And these are result on simulation. We are on the way of testing this algorithm in the real quadrotor. It's not immediate because when we get a simulation, let's say the bridge between good simulation and to test this in real setting is not immediate. So we have to solve some other engineering problems, okay? But we are in the way of testing. You see the behavior is very good. So this is a very good algorithm. Indeed, is one of the best algorithms that we have tested so far. The problem with this algorithm is that it's not robust to wind perturbation. And this is a problem because for outdoors application, you have always wind. So what we did was to design another algorithm, but what we did was to compensate the wind perturbation. So what we did was estimate these wind signals, and I could not, so I will change to, where is it? This one. So this is the work of one of my PhD students. And what we did was trajectory tracking, but using a technique which is called the super twisting technique. Okay, we'll explain briefly what this is. It's based on sliding mode techniques. So let me go quick here. So this is the same. You remember that these are the input signals, the differences, blah, 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 the same. So this is the nonlinear model, blah, blah, blah. The difference here is that the translations of the quadrotor depends on the angles, of course. So we divided the nonlinear model in several subsets, subsystems, and we decided to control separately each subsystem. Instead of trying to control all the nonlinear model, which is very difficult, we have 12 states. So we decided to make a partition of the nonlinear system and control each of them separately. And this was a good idea. So, so the problem of trajectory tracking is those split in several subsystems. So we have here these quantities, 8, 4, 8, 10, and we have several A's here, which are the external perturbations, so wind perturbations. So the problem here is we need to know these perturbations to cancel with the controller. But this is not an easy task. So what we did, and it's, okay, I will skip this because there are some longitudinal motion, et cetera, et cetera. We prove here. If you want more details, I can give you these details after. And we did what we did. Okay, I will. That's the theorem. So just, okay, in order to estimate the wind parameters, we use what we call the exact first order differentiator. And this is a very recent techniques that allows you to estimate the derivative of a signal from the signal. So you maybe in robotics, for example, in robotics guy use some estimators of the derivative, but those are not the good estimators. This is the first real exact estimator. So you can estimate the derivative of a signal. And so it's a very complex equation, but anyway, it works. So what we did was estimate the wind parameter estimation, and then we used this in the control algorithm. Okay? This is just, okay. So these are some simulations in which we changed the tracking signal. Here, for example, what we see is that we don't consider only constant winds, but we test winds, for example, sinusoidal winds. So this is a very interesting setting because most of the work deals with constant winds. But in general, the wind is not constant, nor sinusoidal, but at least it's a step ahead, let's say. And these are the state variables. And now another PhD student is working toward testing this control proposal to the real drone. And we are getting interesting results. Okay? what we are what we have on deck is we are working on the problem of collision avoidance. When, for example, when you have several vehicles flying, so it's very important to avoid collisions. So we are, what a master student did up to now was to use the technique of potential fields, maybe you know this technique, to avoid collisions for, let's say, a swarm of quadrotors. Also, the problem of reconfiguration, for example, if one of the motors for a quadrotor fails, then a quadrotor cannot fly with only 3 motors. It's impossible. But rotor with 6 motors could fly with 5 motors. So the problem there is how to reconfigure the controllers in order to maintain stability and to take the system to a safe position, for example. This is interesting to do. We could avoid many drops or falls or catastrophic falls with this kind of policies. And robust algorithms for wind compensation. Still, we are working on that. Some applications that we were working on, I'm skip this. This is in Spanish, but anyway, I could not make the translation. We have this, which is called the spring wood in Jalisco, which is the biggest wood in the state of Jalisco. And the problem is that each year we have a lot of fires. And this is a problem of the fires on wood, but also the pollution of the city, because the city is beside the woods. So this is a proposal that we have made to the agency in charge of taking care of the wood. And what we want to do is we made several areas so we have the possibility of monitoring with one drone those areas, and also we have the possibility of having recharging towers for drones, etc., etc. We are still waiting for the answer of this agency. Problem is that they don't want to spend money for that. That's a problem. But hopefully we will get some money for them and we will get this project done. Also we have some fire detections. We are working for monitoring fires for the wood as well, because this is to us in the state, in the city of Guadalajara, it's a very, very hurtly situation. Each year, a lot of acres of wood get burned. And this is a drone. Okay, this is a startup that came from our research. No, you know that this is a startup that is working. So this is a proposal. Do you remember the Mindstorm of Lego? Remember that? This is the drone storm. It's the same. So it has, but this is a startup, and we thought that this is interesting also for colleges and how do you say bachillerato? No? High school. Okay, high school. To know or to get acquainted with this kind of technologies also. So the commercial is that if you want one of those systems, please contact me after the talk. This is a joke, but not really. This is for, also what we are working on is for agriculture applications. For example, we have we did a project for DAO agro-system, which is, I didn't know this, but it's bigger than Monsanto, DAO agro-system, and we did a project for them to monitoring the growth of the corn plants and the health of the corn plants. So they are very, very happy, and they are planning to use this algorithm in several other countries, we hope. This is an application, for example, for grass, and what we do is to determine the quantity of water that the grass needs for different areas. For example, here, the application gives the percentage of water that the grass needs. Okay. All of these are applications that we have performed. Okay, these are some image processing for this. And these are the data generated for the system, etc., etc. Another application that we are proposing for federal fundings, it's a chimera, but anyway, it's a problem that exists in Jalisco. I don't know here, but you have here the high power towers, and some needed people takes the metal from these towers, and these towers collapse. This is an example. This only happened in Mexico, I believe. I don't think that this happened in other countries, but anyway. So the project is to use drones to monitoring the stability of the tower. So in the sense that if some tower starts to be unstable, so they can repair the tower. Okay. And I am finishing now. Okay. This is some lazy uses for drones. For example, Amazon Books delivery. So I don't think this is a good idea for drones, because I think it's cheaper having a guy carrying the books instead of sending books using a drone. But, for example, to carry medicines to isolated community, this is a good application, for example, for drones. Or carrying medical diagnostics and things like that. So this is some future ideas. Previously, some of you asked about the future. Okay, this could be, for example, this is a bicycle, biker, and there is a drone going ahead and giving him information about the cars or whatever can happen. For example, snow cyclops. This is for slopes. You remember that last year it was a big slope in the Himalayas, I guess. A lot of people dead. So if you could get some drones monitoring the frequency of the snow, then the slopes could be prevented. That's a possible application, for example. Perching drones to save energy, and hummingbird and beetle, for example, for farming in difficult areas. Farming, but farming only legal plants. I mean, we are not thinking on illegal plants. Okay, so you can use drones for that. Okay. How many minutes do I have? Okay, some other applications and more if you wish. Let me show you a couple of videos that I was forgetting that. Oh, we have seen this before, I believe. Oh, this is an autonomous flights, and we were monitoring this transformer, electrical transformer. In other video, I have all the image processing, but not here. So, for example, the problem here is that isolators sometimes start to break up, but a human operator cannot detect this. So it's very important to detect the isolators before they can fail. These are the signals, and these are the platforms that we have designed for drones. We have here all the position of the drone. No? The temperature also, we have the measure of temperature here. Let me go faster. And we have the application on a tablet. You can have the FPV, which stands for first person view. So you see 10 minutes, perfect. You see what the drone see. Okay, this is another thing. Okay, I will skip this. No, this is another thing. Sorry. But it's very interesting as well. What happened, I don't know. Let me seek for this. I don't know what's happening. Just a second. This is just a thermal test for the. I don't know where I left. I don't know where is it. I apologize because I don't find this. I mean, it was a video in which we tested live we did some test for carrying. I don't know how do you say that the salvavidas, the life saver. I don't know.
Life vest or like
Li-
a life
life-
vest?
Life vest, not
Yeah.
life vest, the
Yeah.
life vest. Okay, let's say life vest. And for example, a drone is very much faster to arrive to the place
You
where
say
a
the
person
life,
is.
the life buoy or you know, like the round
The round, how
like
do you
in-
call that?
to the ship. Yes. Like
I don't know how do you
like a
say
wheel, you know,
call
like
that
a
in English. Anyway, salvavidas in Spanish.
yeah.
Salvavidas.
We know
And-
what you're talking about. Yeah.
And the drone can carry a salvavidas into the sea, and a drone is faster than a human swimmer, no? And then this is a possible application. We have several videos. But anyway, unfortunately, I don't know what happened. Anyway. I would like just a couple of minutes to talk about if you wish, the drone market, just to finish, because to give all the scenario. So this is what we expect for drone uses in the future. So for example, you see that in agriculture will be more and more the utilization of drones. So be prepared for that. Energy and government, obviously, for security, mainly for security, for monitoring, for example, etc. Media and entertainment, not so much, and others. And this is what we expect for drones in the very near future. Okay, this is the global aerial drone market. You see, this is going to grow, and up to $12 billion. So there is a lot of opportunity for you all here. And this is the partition of up to now registered aircraft. I don't know if yours is here, but not now, not yet. In the next, it will be, for sure. Anyway, so 12 billion in 222. That's the market. So it's drones. Beside all the possible applications, the market is very, very interesting. So we have to be prepared in all the senses if you want to be, a participant of this or an actor of these near futures. Some companies using drones. For example, interesting, EasyJet, you mentioned that EasyJet is using drones for monitoring planes. He mentioned before this application. Very interesting. I have a video somewhere of this. Interesting, for example, they are using drones for the Sagrada Familia completion team, just to monitoring the status of the construction, several other. Okay, pros and cons of drones. Obviously, you can have your own opinion, but anyway. And this is the end of the game. I thank you for your patience.
Thank you, Professor.